Yes, hi dear students. Very good evening to everyone. Welcome back again. Dear students, in the previous session, we have discussed about the preparation strategy of electronic devices, the advantages of gate exam and many things, right? I believe we have gone through that video, right? Now we are entering into some important topics or important questions analysis. Instead of using the word important questions, I could say selected topics, okay? Because as per many students request, okay, I understand students are experiencing some trouble in analyzing energy band analysis. For example, drawing energy band analysis, energy band diagrams with reference to the Fermi levels of PN junctions, MOS diode, accumulation mode, inversion mode, okay, bipolar junction transistors, and finding the static electric field at the PN junction at equilibrium. I understand students are facing some trouble, okay. So in this session, let us have an overview. Instead of going with the overview, let us see some tricks, okay, time-saving techniques or tricks to understand how to go with energy band analysis in a very simple way, okay. Guys, when you are moving towards the energy band analysis, there are some prerequisite concepts you need to recollect, okay. It may be the energy band diagram of a PN junction diode or a BJT or a MOS diode, okay. There are some prerequisite concepts you need to recollect. Like that, if you start any topic, let me say, if you want to go for light emitting diodes, if you want to go for photodiodes, you must be having some prerequisite concepts of generation of carriers, recombination of carriers. You must be knowing some prerequisite concepts of EK diagram, energy versus K vector, momentum vector diagram, which is so-called direct band gap, indirect band gap. Like that, for any specific topic, there are some prerequisite concepts you need to be having. If you're strong in those prerequisites and basics, no doubt that gives you a lot of boosting to enter into the original topic what we have. So before entering into this energy band analysis, first let us concentrate about this energy. What requirement I need in our discussion, I'm going to discuss here. Students, the very first important thing, I hope you know that energy, commonly it is considered as a work done. Am I right here? Energy is considered as a work done. The olden definition, I could say, capacity to do work is energy. The same case, when I said W, work done, I said W, I can say electric energy, W is always equals to VQ. Am I right here? Voltage is equals to work done on a charge. So electric energy point of view, I could say W equal to VQ. Keep this aside. In the similar way, students, we know electric field. Please tell me, dear students, electric field. Whenever I go with electric field, E is equals to, I could say, minus del V, right? If I go into the one dimension, let me say minus dV by dx. True or not, dear student? That is electric field. Relation between electric field versus voltage. Now, guys, if I could have a relation between these two, if I could have the relation between these two, could you please let me know, dear students? So voltage is equals to, that means from here, I could say voltage is equals to energy per charge. True or not, dear students? Energy by Q. If I discuss about electrons, okay, I could say this is minus Q. Now substitute that over here. Now what I'm going to get, therefore, electric field E. Don't forget, this is not energy, this is electric field, okay? Electric field E is equals to, what I'm going to get here, students, minus d by dx into voltage. What is that voltage we have? Energy by minus Q. So what I'm going to get here, d by dx of energy into 1 by Q. True or not, dear students? So let me write here, so into 1 by Q. But because, I meant to say, I'm taking electrons, so negative charge. So negative of negative, we get a positive. That means, what did we understand from this discussion? If I plot a graph between energy versus distance, that means y-axis if I take energy, x-axis if I take distance. Y-axis if I take energy, x-axis if I take distance, then I'm getting a slope. dy by dx is a slope. That slope representing electric field present in a body. Amazing, right? Let me repeat once again, guys. If I take the graph between energy versus distance, y-axis if I say energy, x-axis if I say distance, So if I could get slope for that particular device between energy versus distance, then that electronic device will support electric field. This is very interesting, right? So let me take one example here. Let me take one example. Guys, for example, let me say we have electrons. This is a conducting body, contains a lot of electrons. Let me consider this as an example. Now, guys, assume I'm providing a potential here, voltage, right here. Say this is V applied through the length L. Students, we know that electric field always propagates from positive to negative. So this is the direction of electric field. True or not, dear students? When electric field is in this direction, no doubt force must be acting in this direction on to the electrons, because we know that force acting on electrons is equals to minus Q into electric field. And we say this is the drifting force, correct or not? This force is what, dear students? A drifting force. So because of this electric field, I'm getting the force. Now please let me know, do I have electric field or not? Yes. Now for this design, if I plot the graph, y-axis is energy. Don't forget, x-axis need to be distance. If we take y-axis as energy, x-axis as a distance. Now could you please let me know, dear students, could you please let me know, because of electric field, no doubt, there must be some slope in the energy. Because of electric field, there must be some slope in the energy. True or not, dear students? In what way I'm going to get the slope? Very simple logic. Y-axis represents what? Energy of a particle. Could you please let me know, right side, left side, which side electrons are having high energy? See, we have right side, we have left side. Which side electrons are having high energy? Right side electrons are having high energy. Correct or not, dear students? Because the force is acting on the right side, where electrons will experience a high pressure, high force. Because of that, this to the right side, electrons will experience a high energy. Once it is moving towards the left, its energy will be getting dissipated. So energy graph will be getting decay. So right side energy is very high. Once I'm moving towards the left side, energy will be getting decreased. And we know that if it is ECE, it should be parallel to EV. Correct or not, dear? This is valence band, that is conduction band. And no doubt, EI. EI represents what, dear students? Intrinsic energy level. EC, EI, EV. All the three need to be in parallel. Conduction energy levels, conduction band, valence band, intrinsic energy level, all the three need to be parallel. This is amazing, right? That means what? It is representing what exactly? The energy of electron, because of electric field, the energy band diagram is representing. That means how much energy an electron is experiencing due to electric field. Listen my words carefully. How much amount of energy an electron is experiencing due to electric field. That is clearly specified over here. Due to that, I'm getting the slope in this way. And could you please let me know what is the height of the slope? The height, this height, who decides the height? Very simple logic. Let me say this voltage is high. If this voltage is high, electric field will be high. If electric field is high, this force is high. If the force is high, these electrons will experience a high energy. Correct or not? If electrons are experiencing high energy, now instead of this line, I'll be getting the slope in this way. Because this side, right side, electron will be having very high energy. Its magnitude is getting increased. Therefore, angle will be getting increased. So slope will be getting increased. So the height of the slope completely depends on the voltage responsible for electric field. The height of the slope completely depends on what, dear students? Voltage responsible for electric field. Voltage responsible for electric field. Many PSUs, they have asked to find the height of this slope. Please take care of that. So here, what are the voltage responsible for electric field? V. But don't forget, y-axis is energy. Energy is equals to W, W equals to V into Q. That's why it is Q times V. The height of the slope is nothing but what, Q times V. I think now this is very easy. We can able to draw the energy band diagram over here. One more prerequisite you need to recollect before drawing this here is, you know that, guys, let me say, this is our conduction band, this is the valence band, and y-axis representing energy, energy of the particle. So we know that from electronic devices we studied a lot in the class itself. We know that if I'm moving towards positive y-axis, if I'm moving towards the positive y-axis, this direction represents increasing energy levels of electrons. Increasing energy levels of what, dear students? Electrons. That means if I'm moving towards the positive y-axis, that shows increasing energy levels of electrons. In the similar way, if I move towards negative y-axis, that shows increasing energy levels of holes. Increasing energy levels of what, dear students? Holes. Positive y-axis represents increasing energy levels of electrons. Negative y-axis represents increasing energy levels of holes. Please take care of that. This is very, very important. That is why the lowest energy level of a hole is exactly on EV, valence level, valence energy level. That is the place where a hole is having a lowest energy level, where hole has a rest mass. Hole has what here? Rest mass. Correct or not? Based on this, now you please tell me, in the exam, this is one of the previous questions, okay? You know what examiner has given. This is a p-type semiconductor. This is a p-type semiconductor. So which contains lot of holes, right, dear students? Which contains lot of holes. Now here we are providing a battery or a voltage supply like this. The same way how I have given here, I'm providing a voltage V throughout the length L. Now please tell me, dear students, whenever voltage is applied, no doubt electric field exists. External electric field or applied electric field. Now because of this electric field, no doubt holes will experience their force in the same direction equals to electric field direction. Correct or not, dear students, right? Because positive charge carriers, positive will get repel, holes will be moving in this way. Therefore holes and electric field must be experiencing the same direction of electric field. Therefore I could say force acting on a hole is equals to plus Q into electric field, which is very important. Now we need to plot the energy versus distance graph. So y-axis taking as energy level, y-axis I say energy, and x-axis I say distance. Now speak out, my dear boys and girls. Y-axis energy, x-axis distance. Now tell me, now left side or right side? Which side holes are having high energy? Left side, you're right. Left side, holes experience a high energy, and once I move towards right side, hole energy will be getting decreased. Sir, high energy of a hole is when I move in the positive y-axis or when I move in the negative y-axis. You're right. When I'm moving towards the negative y-axis, hole energy will be getting increased. When I'm moving towards positive y-axis, hole energy will be getting decreased. Correct or not? So here, left side hole energy is very high, indicates here when I'm moving towards negative part of your y-axis, the hole energy will be very small. That is why I need to draw the slope in this way. So this is the place where hole energy is very high, and here the hole energy level is less. Hole energy is very high, hole energy is very less, because it is moving towards the negative y-axis. So this is taken as EV. It should be parallel to ECE, and it should be parallel to what, dear students? EI. That's it. So this is the answer what we got. And here if I go with the slope, note out the height of the slope, Q times V. What V is that? The voltage responsible for electric field. So if you check it out, my dear boys and girls, whether it may be electrons or whether it may be holes, if the voltage is applied in the same potential, in the same polarity, I got the same graph. Have you observed or not? If the voltage is applied with the same polarity, I got the similar graph for both. That is why in the exam, even though it is given as a p-type or n-type, you take electrons as only reference. I think that will be the time-saving method. Instead of saying that going towards the negative side, hole energy is very high, going towards the positive side, electron energy is very high, instead of getting confusion, okay, kill that confusion, man. Finally, we need the result right. So even though these are holes, treat them as electrons. If you treat them as electrons, force will be in this direction. If force is in this direction, right side electrons will be having high energy. Moving towards left side, energy will be decreased. You'll be getting the same answer. You'll be getting what is same answer, just to kill the confusion. If you're comfortable with the topic, I'm so happy. If you're still getting confused, yeah, you need to proceed in that way, better time-saving process. I believe got the point here. So this is the first thing we have. But there is a flaw in this design. Energy band, there is a flaw. There is any drawback? Yes. What is that? I'll show you. Let me take concentration gradient. I say take x-axis as a distance, y-axis. Let me go with the concentration of electrons. Y-axis I say concentration of electrons, and x-axis take it as a distance. Now let me consider we have a concentration gradient here. Now please tell me here, due to the concentration gradient, it is very clear that the carriers can easily diffuse from high concentration to low concentration. True or not, dear students? If the carriers are diffusing in this direction, so this is the direction of electron diffusion. True or not? This is the direction of electron diffusion, and no doubt this will be the direction of electron diffusion conventional current. Yes, that is open secret, already we studied in the class number of times. So I'm going to get a diffusion current here. Now please let me know if I want to plot the energy band diagram. Y-axis is energy, okay, and x-axis if I take a distance. Now could you please let me know, am I going to get any slope? I'm asking you here, am I going to get any slope? No. Why? Why? Because no electric field, man. If electric field is there, then only there exists a slope in energy. Correct or not? If electric field is there, then only there exists a slope in energy. Then only there exists a slope in energy. If electric field is not there, there is no slope in energy, right? So this is the basic rule we have. Slope in energy, y-axis energy, x-axis distance, dy by dx, which is the slope. If slope is not there, electric field should not be there. Or if electric field is not there, there must be no slope. True or not, dear students? That means here electric field is not there because I'm not giving any electric field. If voltage is not there, electric field is not there, and diffusion current is independent on electric field, true or not, then where is the slope? No slope, right? Then no doubt here I'm going to get ECE because slope is equal to 0. And I say this is EV, and I could say this is what, guys? EI. No slope, man. This is amazing, right? No slope. We are very happy, but I want to ask a small question. This was a question raised by one great scientist, okay? The question here is, what this is representing? Conduction band represent electron energy levels, free electron energy levels. Valence band represents whole energy levels. Now my question here is, as per energy band diagram, maybe left side or maybe right side, electrons are having same energy. That is what it is representing. I am repeating once again, guys. Maybe left side or maybe right side or throughout the distance, electron energy level is maintained same. That means if left side and right side, electron is having same energy, that shows the same potential. If both are having a same potential, how a particle can move from one place to other place? Correct or not? That is what it is showing. But unfortunately here, particles are moving because there is a potential gradient, there is a slope, potential difference. Whenever high potential or low potential, or we say concentration gradient, okay? Better to use the word concentration gradient. So between high concentration to low concentration, the carriers are easily getting diffused. Indicates the carriers are having some difference, concentration difference, energy level difference. But unfortunately, this is unable to show that difference. So this is a flaw, what a scientist exhibited. What a scientist expressed, okay, on this energy band analysis of valence band, conduction band, intrinsic levels. Interesting. And moreover, interesting point here is, after some time what happens, guys, once electrons are getting diffused from high concentration to low concentration, what happens? You please tell me. Once electrons are getting diffused from high concentration to low concentration, x-axis is distance, y-axis is what here? Concentration of electrons. Now speak out, guys. If electrons are getting diffused from high concentration to low concentration, here there exists what here? Positive ions, am I right here? And here what I'm going to get? Negative ions. Electrons, I'm going to say diffused. Atom lose an electron, positive ion. Atom accept an electron, negative ion. So when positive and negative ions are getting separated, my goodness, there exists electric field. Yes, electric field always move from positive to negative. This is interesting. And this electric field, I'm not giving an electric field. Am I giving any electric field? No, I'm not giving any electric field. That is electric field generated internally. We call it as a built-in electric field. So we say EBI, built-in electric field. When I get an electric field, under some distance we say L, no doubt, I'm going to get a potential. We say built-in potential. Wonderful, wonderful. I'm getting a built-in potential. So whenever electric field is in this direction, and these are the particles which are so-called electrons, there will be some force. Correct or not? With respect to electrons, if electric field is there, there will be a force generated opposite to electric field. Opposite to electric field. That force is called a drifting force. Correct or not? Drifting force. So this is a built-in force acting on electrons, which is nothing but a drifting force. Drifting force. Very interesting. Drifting force. Now this drifting force opposing further diffusion of electrons. My God. This built-in force opposing further diffusion of electrons. So, for example, I say, guys, if electrons are diffused in this direction, I could say this is electron diffusion current. If the force is in this direction, I could say this is electron drift current. Correct or not? Because we are using the rules of conventional current. So, interesting fact here is this drifting opposing the diffusion. Drift current opposing the diffusion current, or I say drifting force opposing further diffusion of carriers. So here what I'm going to get, the total current, which is so called drift current plus diffusion current. Drift current plus diffusion current. Interesting point here is at equilibrium, whenever I say equilibrium, no doubt total current equal to 0. That means no current. Why it experience equilibrium? Come on, man. The force is opposing further diffusion of carriers. At a particular moment, this force is sufficient to stop the diffusion of carriers. At a particular moment, this force is absolutely sufficient to stop the diffusion of carriers. Once the diffusion of carriers are stopped, the total current equals to 0. Now tell me here, if there is no further diffusion of carriers, no further increase in positive ions, no further increase in negative ions, indicates positive ions are becoming fixed. Negative ions are becoming fixed. Indicates electric field is becoming fixed. That means at equilibrium, what electric field I'm getting here is the built-in electric field is fixed. Instead of saying fixed, okay, I can say static. Static. Because no further increase in the, I'm going to say, electric field. So it is becoming what, dear students? Static. Static built-in electric field. No current, don't forget. It is absolutely under equilibrium. Now here the conflict. If I plot the energy band diagram, let me say y-axis is energy, right? And x-axis say distance. If I plot the energy band diagram right now could you please let me know, my dear boys and girls, what I'm going to get here? Let me change the color. Okay, what I'm going to get here. Students, now please tell me, do I have electric field? Yes, I have electric field. If I have electric field, slope exists. If I have electric field, what here? Slope exists, because dy by dx, d of energy by dx, slope exists. Now, due to electric field, force is in that direction. Now, due to the electric field, electrons are having high energy at the right side or left side. Due to electric field, electrons are having high energy at right side or left side. Speak out, guys. You're right, right side. So right side electrons are having high energy. Therefore, I'm going to get the slope in this way, which is none other than EC. If EC is in this direction, no doubt this is the AI must be maintained with the same slope, and this is EV must need to be maintained with the same slope. And no doubt this height of the slope is nothing but Q times VBI, because the voltage responsible for electric field is nothing but height of the slope. Now what is this energy band diagram representing? I'm drawing this at equilibrium. Yeah, don't forget the word, okay? I'm drawing this at equilibrium. Why? Because at equilibrium, voltage is constant. At equilibrium, electric field is constant. Electric field is there, and that electric field is stable. So what this is showing, even at equilibrium, right side electron has high energy, left side electron has low energy, indicates electron can easily propagate from high energy to low energy because of energy gradient, because of potential gradient. That is what this is showing. But what result I got? At equilibrium, total current equal to 0. Why? Because the built-in force balancing the diffusion. The net current equal to 0. That is the basic principle of equilibrium. Now this is absolutely showing a contradiction result to what is happening exactly. That is what a scientist raised the question. I believe he got the point or not. That means what? If you check it out, all the previous history, this diagram, or this diagram, or this diagram, or this diagram, if you check it out, conduction band slope, or conduction band energy levels, valence band energy levels, you know what exactly they're representing? The energy of the particle due to electric field, that's it. If an electron is having an energy because of electric field, where is that energy? How much is that energy? This energy band is representing. But these are not representing the energy level or a net energy acting on electrons. Net average energy acting on electrons, I'm sorry to say, these are not representing. So ECE unable to represent the net energy acting on electrons. EV unable to represent the net energy acting on holes. Then based on this, how can I design the electronic system? So these are all very important contradictions what arised in case of the concept of diffusion system. So to avoid this limitation, you know, we got a beautiful concept called Fermi energy levels. You know, guys, you need to study a lot regarding the Fermi energy level. Please take care of that. So this limitation was absolutely overruled by Fermi energy levels. You know, Fermi energy will discuss the condition of equilibrium. Fermi energy discuss the highest energy of a particle even at 0 kelvins. Fermi energy discuss the highest velocity of a particle even at 0 Kelvin. Fermi energy discuss concentration of carriers in the conduction band, concentration of holes in the valence band. And Fermi energy discuss the net average energy acting on a particle. So that is the real energy, I could say, to understand the net energy acting on a particle. The energy may be because of electric field, maybe because of light, maybe because of heat, maybe because of magnetic field, maybe because of any other sources and resources acting on electron. I just don't care. Once any energy acting on electron, what is the net energy acting on electron? Where is that level? Where is the position of an electron because of that energy? You can identify by using a Fermi energy level. So Fermi energy level play a very vital role in case of our semiconductor devices, or we say solid state electronic devices. So guys, you need to recollect this. So as per our understandings of Fermi energy levels, okay, in our electronic devices, so at equilibrium, there must be no slope in the Fermi energy. Here also the same case. Y-axis is energy, x-axis is distance. So if slope equals to 0, I'm repeating once again, guys, if slope equals to 0, understand that the device is under equilibrium. If there exists a slope in the Fermi energy level, understand that my device is under non-equilibrium. These two are very important factors you need to recollect. If electric field is there, there exists a slope in ECE, EI, EV. If non-equilibrium exists, there exists a slope in the Fermi energy level. If equilibrium is there, slope in the Fermi level is 0. If electric field is not there, slope in the energy itself is equal to 0. It may be EC, EI, or EV. Guys, okay? So let us take our examples again. Here, I want to include Fermi levels also. Please take care of that. The same example I'm repeating, okay? Now have a look. Here what I have, guys, first case I am taking electrons. Am I right, dear students? Electrons. And here, holes. I hope you guys understanding, and if you find this is interesting, okay, try to copy down the important points, okay guys? Because this is 1 hour video. So I want to make the task easiest way. I want to show you the task in easiest way in 1 hour. Okay, so that is why I'm taking, or I'm considering only the very important points what we need to understand carefully. Now guys, anyways, here, have a look. Student, this is positive and negative. Yes, the same voltage I'm applying here, positive and negative, right here? Fine. Now please tell me, dear students, so y-axis is what here? Energy, and x-axis distance. So y-axis energy and x-axis distance. The same case here also, x-axis is distance, y-axis is energy. Right, yes? Now speak out, my dear boys and girls. First let me concentrate on this part. So no doubt, electric field will be in this direction. Because of that, force will be acting on electrons in this direction Fn. Now speak out guys, please let me know, dear boys and girls, everybody in the class, right side or left side? Which side electron will be having high energy? Right side. Therefore, this is the slope, which is EC. And no doubt, this is what, dear students? EI. And this is what, guys? EV. Correct or not, dear students? EV, right? Wonderful. Don't forget, right side, electrons will be experiencing a high energy because of electric field, okay? Now I want to draw Fermi energy. Now could you please let me know, do I have Fermi energy here? Yes, man. What is that Fermi energy represents? The Fermi energy represents here net energy acting on electrons. Interesting fact here is, the only energy acting on electrons is only because of electric field, correct or not? The only energy acting on electrons in this case is only because of electric field. Correct or not? Now net energy of electron is high at what side? Right side. Is it under equilibrium? No, it is not under equilibrium because I am getting current, drift current. If I am getting current, it is not under equilibrium. As it is not under equilibrium, there will be slope in the Fermi energy. And one more interesting point here is, the net energy acting on electron is high at the right side. Once I am moving towards left side, net energy is low. And moreover, this is electrons. Electrons indicates, we can say, conduction band. Energy levels will be very near. Fermi level is very near to conduction band, correct or not? Therefore, right side, electron energy is very high. If I move towards left side, electron energy decreases because Fermi level represents net energy acting on electron. Lucky point here is the net energy is only because of electric field. Now, this is the Fermi level, we say, based on these electrons here. That is great. I believe you guys got it right now. Now device is not under equilibrium. Why? Because even Fermi level is having a slope. Now here I included what here? Fermi energy level. Now in the same case here, you please tell me. Yes, guys. So same situation. Electric field is in this direction. No doubt force is in this direction acting on holes. Right or wrong, dear students? Therefore, I'm very happy to say, whenever force is high here, left side, electrons will, holes will be having high energy. If hole is having high energy, it should start from down because moving towards negative side, hole's energy will be very high. Correct or not? So moving this way, which is EV. So no doubt it should be what here? EC. And this could be what here? EI. Now please tell me about Fermi energy level, guys. Please tell me about Fermi energy level. The same situation here, I am representing with reference to what, dear students, holes. So holes indicates what? Fermi level must be near to valence band. If I say p-type, the Fermi level must be near to what, dear students? Valence band. And no doubt, left side, hole energy is very high because the net energy, the only energy here acting on hole is because of electric field. So left side, hole energy is very high. Moving towards right side, hole energy is low. So this is the Fermi level with respect to holes. But take care, near to the valence band, because whenever holes are taken as a majority, I understand we need to take it as a p-type semiconductor. I believe you got the point. Now let us check it out the case in case of diffusion. That was what we suffered a lot in the previous case, I believe. Let me go with the concept of what here? Diffusion. Now speak out, guys. Y-axis is what here? Concentration. Concentration of electrons, right here? Concentration of electrons, and x-axis is like a distance. Now this is the case, right? Concentration gradient. Now what is the first case? Please tell me, dear students, electrons are getting diffused from high concentration to low concentration. Yes. Now if I plot the graph between energy versus distance, so x-axis distance, y-axis is energy of electrons, okay? Now please let me know, dear students, okay, let me know. So there is no electric field. If no electric field, no doubt, this is the ECE. No electric field, no doubt. This is what here? EV. No electric field, no doubt. This is EI. EI. This is good. But electrons are having high energy in the left side. Why? Come on, man. It is getting diffused from high concentration to low concentration. What do you mean by that? Left side, electron is experiencing some sort of high potential or high energy. High energy is at the left side, moving towards right side, energy is getting dissipated. So the net energy acting on electron, who is going to represent, guys? Yes, you're right, Fermi energy. And moreover, electrons are getting diffused from high level to low level, indicates there exists a diffusion current. If diffusion current is there, it is not under equilibrium. If it is not under equilibrium, there will be slope in the Fermi energy. Therefore, left side electron energy is very high, right side energy of electron is getting decreased. So left side electron energy is high. If I move towards right side, electron energy is getting decreased. Wow, this is the way how I can go for Fermi energy with reference to electrons in this situation. My God, this is amazing, right? So that is what exactly representing the net energy acting on electrons. So once the particles are participating in current, what is the net energy acting on particle, acting on that particular carrier? Yes, man, I have a weapon right now. It is Fermi energy level. Fermi energy level, thanks to the great engineering, right? In the similar way, after some time, at equilibrium, I say, no doubt, please let me know, guys. There is gradient you have, concentration, okay, of electrons, and this is distance. Electrons are getting diffused from high level to low level. Here I'm going to get what here? Positive ions, and here I'm going to get what here? Negative ions. Because of the positive and negative, yes, man, I'm getting a built-in electric field, no doubt, built-in force, and this is the distance, L. Because of that, I'm getting a force, which is a built-in force, or we say drifting force. Now if I plot the graph, y-axis energy, x-axis distance, energy versus distance. Yes, right? Now please let me know, my dear boys and girls, please let me know. So right side, electron energy is very high at the right side, right? Therefore, this must be the slope, which is nothing but EC. This must be the slope, which is nothing but what here? EV. And this must be the slope, which is for EI. Because right side, energy of electron is high. Left side, energy of electron is getting decreased because of electric field. I'm repeating the word because of electric field. But don't forget, everything is under equilibrium, am I right? Whenever I say equilibrium, no doubt total current equal to 0 and electric field is static. So slope exists for EC, EI, EV, but take care, there must be no slope. There must be no slope for Fermi energy. That's why Fermi energy need to be drawn straight. There is no slope, man, no slope. So this is taken as simply EF, no slope. So this is representing that no current. Left side net energy of electron is equal to right side net energy of electron. So left side, right side, the net energy of electron is same. So it is balanced. Whenever it is balanced, no gradient. If no gradient, how a charged particle can move from one place to other place? Therefore, total current equals to 0. What a Fermi level, man. So because of that, I could able to identify the position of a particle when it is participating in the current. So that Fermi energy level played a very important role here. So please take care. For example, let me say, if you recollect the concept of Fermi energy level, I believe you know that. If doping increases, I think you can understand. If I say N-type semiconductor, Fermi level move towards. Fermi level move towards what, dear students? Conduction band. In the similar way, if it is P-type semiconductor, Fermi level move towards valence band. You need to recollect all this, okay? So if doping increases, if it is N-type semiconductor, Fermi level move towards conduction band. If it is P-type semiconductor, Fermi level move towards valence band. Whereas if temperature increases, Fermi level move towards center of energy gap. That means move towards intrinsic energy levels. The center of energy gap is like an intrinsic energy level. So if temperature increases, Fermi level move towards intrinsic energy level. Understand? It may be N-type or it may be P-type. Not advisable, okay? We go with the word of critical temperature, I believe you know that, or Curie temperature, which is not advisable. But don't forget, if doping increases, Fermi level move towards conduction band for N-type. Doping increases, Fermi level move towards valence band in P-type. One important point here is, let me say, I dope heavily, extreme heavily. If I dope extreme heavy, then no doubt in N-type semiconductor, Fermi level move into the conduction band. In N-type semiconductor, Fermi level move into the conduction band. in p-type semiconductor, Fermi level move into the valence band. So because of a particular doping, Fermi level moving towards or into the conduction band of n side, into the valence band of p side, okay, into the valence band of p side, then that type of semiconductor is called degenerative semiconductor. I repeat, degenerative semiconductor, and that type of doping is called as a degenerative doping. GATE 2023 question this is. Okay, degenerative doping, or we say degenerative semiconductor. Please take care of that. Now let's have, one more requirement here, because these are all the prerequisites if you want to draw the energy band diagram of a PN junction or a MOS diode or a bipolar junction transistor or any question they're going to give you in the exam. One more requirement under energy band diagram is work function. So what is work function? If you ask me, guys, amount of energy required to bring an electron from Fermi level to the vacuum state. For example, I say, see, this is the vacuum or vacuum. Every body will be having a vacuum energy level. Am I right here? Let me say this is the Fermi level of a particular body. So assume a particle energy is here. So how much amount of energy I'm supposed to provide to bring this particle to its vacuum state? That energy is given as the work function. So this distance is taken as a work function. The amount of energy required to bring an electron from the Fermi level to its vacuum state is work function. One more thing we have that is called electron affinity. Electron affinity. What is the meaning of electron affinity? Amount of energy required to bring a particle from conduction level to the vacuum state. That means, for example, I say this is the vacuum state, which is E naught. This is ECE, okay? And say this is EF. Say this is EC, EV, okay? EV. So how much amount of energy required to bring an electron from Fermi level to vacuum level is called work function. How much amount of energy required to bring an electron from EC level to vacuum state, that is called electron affinity, denoted with xi, electron affinity. So electron affinity, work function. Of course, we studied this from 10th class, 12th and 11th classes, I understand. You please try to recollect this, very important. Let me take one example. At least I believe you get a conviction here. Guys, if it is metal, let me say this is a metal, okay, metal. Metal is a conductor, first group, second group, third group. And this is a semiconductor, a metal and a semiconductor. So that is the vacuum energy level. Okay, then no doubt, you know that in case of conductors or metals, conduction band, valence band overlaps. Whenever conduction band, valence band overlap, then how can I identify the energy of electron? The energy of electron, no doubt, I have a weapon. What is that? Fermi level. Fermi level identifies the energy of an electron. Fermi level discusses the energy level of a particle. Fermi level represents the highest velocity of a particle, the position of a particle, equilibrium or inequilibrium condition of a particle. Guys, understanding? Because net energy, average energy acting on a particle given by whom? Near Fermi energy level. So this is enough in case of conductors, because conduction band, valence band overlap, man. Am I right? Now, tell me, my dear students, so the amount of energy required to bring an electron from Fermi level to its vacuum, this is nothing but work function, I say, phi m. Phi m represents work function for a metal. In the similar way, for semiconductor, phi silicon, I say, assume it is silicon semiconductor, phi silicon, the work function. Whereas this is taken as xi, electron affinity. Electron affinity. So for your notes purpose, I have given even here energy required to take an electron from EC to vacuum level, which is none other than, tell me, dear students, electron affinity. I believe you got some idea. Now let us take one example which includes previous questions again. Students, consider a metal to semiconductor contact. Oh my God. There is a contact. There is a contact between metal to semiconductor, such a way that the work function of a metal is greater than work function of a semiconductor, whereas semiconductor is n-type. Now they are asking to draw energy band diagram. There are 4 options. Out of 4 options, which option is correct? Okay, it may be the question of Bob Atomic Research Center, maybe DRDO, maybe GATE, or maybe engineering services. Listen the question carefully. Take a metal to a semiconductor. contact, and examiner has given a condition that metal work function greater than semiconductor work function. Condition is what? The semiconductor is n-type. Now we need to draw the energy band diagram. How it going to get? Interesting, man. So let us see individually. I mean to say isolated. This is like isolated energy levels. Isolated energy levels. Isolated energy levels. I want to go with a separate, isolated. Okay, now please tell me, dear students, he has clearly given that phi m greater than phi si. That is why this is larger. Phi m is larger compared with the phi si, phi silicon. Okay, that is why I have drawn in this way. I believe you got the point. Phi m must be larger than phi si. Moreover, this is n-type. As it is n-type, Fermi level must be near to the conduction band. And no doubt there is an energy gap in case of semiconductor. Energy gap. This is energy gap. Now speak out, everybody in the class. Please speak out. I think that is representing high concentration. This is representing low concentration. Here itself I can able to understand a concentration gradient I have. Because it is a high energy, high concentration, low concentration, there is a gradient. Because of that gradient, natural temperature is sufficient to make the carriers can easily jump from high level to low level. Excuse me, correct or not? Now speak out. Whenever carriers are diffused from high concentration to low concentration, I believe here I'm going to get positive ions. What ions, guys? Positive ions. Oh my God. This is what type of semiconductor, guys? See, this is metal, am I right? This is metal. This is metal. Metal. And this is N-type semiconductor. It is what, dear students? N-type semiconductor. Sir, if that is positive, no doubt, here it behaves like what, dear students? Negative ions. Positive ions as well as what, dear students? Negative ions. Now a small question I want to ask you. Now, these are isolated, they are separated. Now I need to join together. Once I join, I need to draw it equilibrium. Once I join together, I need to draw it equilibrium. Can you please guess what I'm going to get here? Can you please guess here? Simple logic. N-type semiconductor, and this is metal, positive and negative. Don't forget, N-type semiconductor, positive ions, indicates depletion region. Please recall it, guys. N-type semiconductor, positive ions. That means atom donate electron. It is nothing but depletion region. That means here I'm getting a depletion region. This is interesting. I thought there exists a depletion region at a p-n junction. Surprisingly, this is not a p-n junction. One is a metal, other is N-type semiconductor, but still I'm getting a depletion region. This is amazing, right? Now what I'm going to get here, please tell me at equilibrium. Let me go with equilibrium. Whenever I say equilibrium, Fermi level must be straight line. Come on, man, there must be no slope in the Fermi level, right? So the Fermi level of metal and the Fermi level of silicon, yes, no doubt, need to be straight. Need to be straight. Next, excuse me, this is negative. That is positive. So I believe you can understand electrons' point of view. This is the direction of force. This is the direction of force acting on electrons. I'm repeating electrons' point of view. This is the direction of force acting on electrons. Indicates left side electron energy is high. Right side electron energy decreased. Left side electron energy is high. Right side electron energy decreased. Excuse me, who discussed this? Left side energy of electron is high. Right side energy of electron is low because of force. Who discussed this? Is Fermi level discuss this? No, Fermi level never discuss. Which will discuss now here is only EC level and EV level. Correct or not? Because the energy of a particle because of electric field discussed by ECE, EV levels in a proper way. So I believe you got the point. So this is the direction of what here? Electric field. This is direction of electric field. Electric field move from positive to negative, and the force is in this direction because of electrons' point of view. Now tell me, dear students, as the force is in this direction, electric field is in this direction, no doubt how the EC, EV must be there. Lucky point here is no EC, no EV in case of conductors. We have EC, EV only in case of semiconductors. Therefore, here in case of semiconductor, no doubt, tell me, dear, left side energy is high, right side low. So left side energy is high, right side is low. There is a slope, and here no electric field, so no slope. Here slope is there because electric field is there, and here no electric field, here no slope. This is nothing but EC. EI should follow the same. So EI. Wow, this is super nadir. EI. and EV must be following the same. This is what, dear students? EV. And of course, this is like a, a contact. This is the contact. Which contact? Between metal to N-type. Wow. Here I'm excellent, man. This is correct or not, dear student? There is a barrier. That is called, depletion region. There is a barrier. Guys, understanding or not, we call it as a barrier potential. And this type of semiconductor is called Schottky diode. This type of semiconductor diode is called as what here? Schottky diode. And the height of this potential from here to here, let me say phi bi. Schottky built-in potential, or simply we call it as a Schottky potential. Schottky built-in potential, or we say Schottky potential, Schottky diode. Arey man, I really don't know about the name, but a very simple point I have, phi m greater than phi silicon. Could I able to draw the energy band diagram? Yes, man, we have drawn. This is the beauty of engineering and technology. You guys understanding or not, dear students, right? Now, in a similar way, let me go with a p-n junction. Sir, just now we have seen the junction between metal and N-type semiconductor. Now I'm going to go with the junction between N-type and P-type semiconductor. Sir, N-type semiconductor, I hope you know that there exist positive ions. Correct or not, dear students? Immobile ions, we say positive ions. P-type semiconductor has what here? Negative ions. Let me consider equilibrium. Let me go with the case of what, dear students? Equilibrium. Is it okay? Now, speak out. My dear boys and girls, speak out. So, no doubt, here there is an electric field, which is called as a built-in electric field. True or not? Because of electric field, force will be in this direction, which is nothing but force acting on electrons, which is a built-in force acting on electrons. There is a force. Excuse me, correct or not, everybody in the class? Everything is under equilibrium. Sir, whenever I use the word equilibrium, no doubt, you can understand there will be no slope in the Fermi level, so it must be straight line. Fermi level must be straight line, correct or not? No slope in the Fermi level. So it is N side, so let me say EFN. That is P side, let me say EFP. Guys, I believe you got the point or not, dear students? Now, speak out, everybody in the class. See here, I'm just having a small separation here. I'm separating this because, I'm sorry. What happened? Entertainment. So I'm sorry, dear, there is a technical glitch. I'm so sorry for that. I'm so sorry. So anyways, let me redraw this. So this is our p-n junction, right, dear students? This is like N-type semiconductor, P-type semiconductor. Carefully listen. N-type semiconductor contains what, dear students? Positive ions. Here we have positive ions, right, dear students? And no doubt, here we have what here? Negative ions. Please understand carefully, my dear boys and girls. Negative ions, right? Now, everything we want to maintain under equilibrium because I want to follow at equilibrium case. Now at equilibrium, there exists what, dear students? Static electric field. So electric field is moving in this direction, which is nothing but a built-in electric field, or we say static electric field. And this is the direction of what, dear students? Built-in force acting on electrons. Static electric field and built-in force. Now speak out, guys. At equilibrium, no doubt, Fermi level, there will be no slope. There is no slope in the Fermi level for sure. So this is the Fermi level of N-type semiconductor, the Fermi level of P-type semiconductor, right? Now, please tell me, in this region, we say depletion region, correct or not? In this depletion region. Yeah, Now speak out. What is happening? I think there is electric field. But here no electric field. Excuse me, correct or not? This is a neutral region. There is no electric field. Neutral region, no electric field. Sir, whenever no electric field, I think there will be no slope in ECE. ECE. N-type semiconductor, Fermi level must be near to the conduction band. No slope in EI. EI. No slope in EV. No slope in EV. Take care of that. Very, very, very important. No slope in EV. Guys, okay? Because it is N-type semiconductor. In the similar way, please tell me, dear students, P-type semiconductor, this is a neutral region. No slope in EV. No slope in EV. Am I right, dear? No slope in EI. No slope in EI. Right? And there is no slope in EC. No slope in EC. And please tell me, dears, everybody, this is a built-in force, okay? Built-in force. Now, guys, could you please let me know, everybody in the class, because of electric field, right side electron is having high energy. Once I'm moving towards left side, electron energy decreases. So right side, electron has high energy. Once I'm moving towards left side, electron energy decreases. Right side, it has high energy. Once I move towards left side, electron energy decreases. That's it, man. This is what exactly we got the energy band diagram. And no doubt here, I need to merge both. Guys, okay, energy band analysis of your PN junction. And no doubt, the slope, you know, this slope is nothing but, the height of this slope is nothing but Q times VBI, built-in voltage. Because due to what voltage I got this electric field, the slope is belonging to that. In the similar way, if I go for bipolar junction transistor, for example, I say N-type semiconductor, NPN transistor. So N-type contains what, dear students? Positive ions here. See how fast we can draw. You please try to understand. Try to grab it, which is very important. P-type semiconductor contains what ions, guys? Negative ions. Again, P-type contains what ions, guys? Negative ions. And N-type contains what, guys? Positive ions. See, try to save a lot of time, man. That is very important. Right? So here, you please let me know. Yes, this is the depletion width, what we have for emitter junction. And this is the depletion width, what we have for collector junction. Guys, right? Now, speak out, everybody in the class. At equilibrium, I want to study everything under equilibrium. Now, whenever I say equilibrium, this must be straight line, right? I'm going to say no slope in the Fermi level. This is EF, simply EF. Now, speak out, boys and girls. This is N-type semiconductor. Fermi level is very near to the conduction band. But I think you know emitter. Emitter must be having more doping. Whenever doping is high, Fermi level near to the conduction band. Whereas this is P-type semiconductor. Fermi level, doping is less. Doping is less indicates Fermi level is slightly away from conduction band. It's away from valence band. So that means there must be some difference you need to represent. Fermi level is away from valence band. In the similar way, this is N-type semiconductor. Collector is moderate doping. Higher doping compared to the base, lesser doping compared to the emitter. So that's why slightly higher, slightly higher, we need to represent here, which is nothing but what here? EC. This is nothing but what here? EV. Don't forget about that. Now, EC, so EV must be here. The same energy gap, EV, EC must be here. The same energy gap, EC, EV must be here. Right? Now speak out, boys, everyone in the class, please tell me. So electric field move from positive to negative. This is the electric field. Therefore, this is the force, built-in force or a junction force acting on electrons. And no doubt, electric field is moving in this direction. Therefore, this is the force acting over here, junction force acting on electrons. This is emitter junction, that is what a collector junction. Now speak out, guys. Right side, force is high. So right side, electron energy is high because of electric field. So this is the slope what I got. This is the slope what I got. And here left side, electron energy is high because of electric field. So left side energy is high. Left side energy is high. Oh my God. This is very easy, right, dears? So this is what we got as energy band diagram at equilibrium NPN transistor. In the similar way, go with this. This is a previous gate question. Previous gate question and at a very high concentration. Carefully listen, dear students. So this is P-type semiconductor. We have negative ions, negative ions, negative ions. N-type semiconductor, what, dear students? Positive ions here, right? Positive ions. Here N-type contains positive ions, no doubt, positive ions. Correct or not, students? It has positive ions. It is also N-type, but take care, it is N plus. Indicates doping is very, very, very high. Doping is very high. If doping is very high, depletion width will be very low. Here it is N plus. This is interesting. Doping is high, depletion width will be low. Whereas it is P plus plus, extreme heavy doping. If extreme heavy doping, depletion width will be damn very low. Damn very low. Yes. Now, please let me know at equilibrium. Examiner is asking to draw the energy band diagram at equilibrium. 2019, I believe, the previous gate question, okay? They have given 4 options. I'm not showing any options here. Directly we can do here. So at equilibrium, there will be no slope in the Fermi energy level. Excuse me, my right, dear students? Now, speak out, guys. So here, yes, I have electric field because of depletion. Electric field because of depletion. Here I have electric field because of depletion. Yes, wonderful. Now speak out, boys and girls. I need high concentration. This is P-type semiconductor. So Fermi level must be near to valence band. So this is EV. N-type semiconductor, Fermi level must be near to conduction band, which is EC. So if it is EV, so this must be what here? EC. If it is EC, so this must be what here? EV. Super. Now it is N plus. N plus indicates what? N plus indicates what? Heavy doping. Indicates Fermi level must be near to conduction band. That's why I am drawing EC level near to conduction band. So if it is EC, so EV must be here because the same gap need to be maintained. It is P plus plus, array man, P plus plus indicates extreme heavy doping. Degenerative semiconductor. Thank you so much. Therefore, Fermi level must be inside the valence band. Therefore, valence level must be drawn here. This is valence band, EV. Therefore, this will be what, dear students? EC. Because Fermi level must be drawn inside the valence band. Now speak out, everybody in the class. Now speak out. Students, left side force is very high. Correct or not, dear students? So left side force is very high. Slope must be in this way. The same slope must be followed. Here, please tell me, electric field always move from high level to low level. I'm repeating, electric field is always moving from high level to low level. Here, doping is very high, so high positive ions. Therefore, force must be in this direction. Therefore, this is the way I'm getting the force. Whereas here, you please tell me, this is the direction of the force. So this is the direction of the force here. This is the direction of the force here. My God. Amazing, Nadia. This is one of the previous gate questions they have asked. So yes, we can easily draw the energy band diagram of this question like P, N, N plus and P plus plus device. So like that, I think time is up, I understand. So in this way, my dear students, go through lot of concepts, go through lot of numericals. So once you start with energy band, complete all the energy band analysis, including your MOS diode or MOSFET. If you start electric field profile, do all the concepts of electric field profile. If you're studying about p-n junction current, study about all the currents, drift current, diffusion current, p-n junction current, photodiode current, light emitting diode current, okay, Zener diode current, BJT current, and as well as MOS current and VA characteristics. Like that, you follow the rules and regulations in a proper way. If you know the basic concepts, absolutely, you can do miracles for sure. Anyways, thank you so much for attending this wonderful session, dear. See you very soon. Have a wonderful life. Have a great time. Jai Hind.